For more than half a century, one question has never disappeared. What really happened on Apollo 11? Millions watched as humanity took its first steps on the moon, but behind the famous images lies a story far more complex, risky, and astonishing than most people realize. From the final moments before launch to the tense descent onto the lunar surface, this is the true story of the mission that changed history forever. Before we begin, make sure to like this video, subscribe to the channel, and turn on notifications for more fascinating space documentaries. Now let's travel back to July 1969 and uncover what really happened during the first moon landing. In the years before Apollo 11 leaves Earth, the planet exists within a period of rapid technological change and intense international attention. Large populations follow developments in science and engineering with unusual interest. Newspapers, radio broadcasts, and television reports regularly discuss rockets, satellites, and human spaceflight. The idea of reaching the moon is no longer limited to fiction or distant dreams. It becomes a practical objective supported by governments, engineers, scientists, technicians, and industrial workers spread across many regions of the United States. Earth itself remains the starting point of every part of the story. The oceans, continents, mountains, deserts, and cities of the world form the background against which the mission takes shape. Human beings live entirely within the thin layer of atmosphere surrounding the planet. Every machine, every test facility, every factory, and every launch site exists beneath this protective envelope of air. Space remains beyond daily experience for nearly all people. The moon is visible in the sky, yet it remains a distant place that no human has ever visited before the Apollo program. The scientific understanding required for a lunar landing develops gradually across many decades. Physicists study motion, gravity, and energy. Chemists investigate fuels and materials. Engineers design machines capable of operating under extreme conditions. Astronomers map the moon and examine its surface through telescopes. Geologists study impact craters on Earth and compare them with features visible on the lunar surface. Knowledge accumulates slowly through observation, experiment, calculation, and testing. During the middle years of the 20th century, advances in rocketry make travel beyond Earth's atmosphere increasingly realistic. Earlier generations developed the principles of liquid fuel rockets. Researchers refine engines capable of producing enormous thrust. Military projects contribute technical experience while scientific missions demonstrate new capabilities. Each achievement reveals additional challenges. Reaching space is difficult. Remaining in space is difficult. Returning safely to Earth is equally difficult. In October of 1957, the launch of the first artificial satellite marks a major moment in human history. A spacecraft successfully enters orbit around Earth. Soon afterward, additional satellites follow. Human spaceflight becomes a serious objective. Competition between the United States and the Soviet Union encourages rapid development. This rivalry influences political decisions, public funding, and scientific priorities throughout the following years. As the space age progresses, both nations achieve important milestones. Humans enter orbit around Earth. Spacecraft travel farther from the planet. Missions test life support systems, navigation methods, communication equipment, and techniques for operating in weightlessness. Every success expands knowledge. Every failure reveals weaknesses that must be corrected. Engineers learn that spaceflight requires extraordinary attention to detail. Small errors can produce major consequences. The moon gradually becomes the next destination. From Earth it appears familiar. Its bright surface has been observed throughout recorded history. Yet many basic questions remain unresolved during the early years of lunar exploration. Scientists debate the nature of the surface. Some wonder whether spacecraft might sink into deep layers of fine dust. Others predict a firmer landscape shaped by impacts and volcanic activity from the distant past. Robotic missions begin providing clearer information. Uncrewed spacecraft play a critical role. They photograph the lunar surface, measure environmental conditions, and test landing techniques. These missions reduce uncertainty. Images reveal craters, plains, mountains, and valleys in increasing detail. Scientists identify locations that appear suitable for future human landings. Knowledge grows steadily, replacing speculation with direct observation. Meanwhile, the United States commits itself to the goal of landing humans on the Moon and returning them safely to Earth before the decade ends. Achieving this objective requires an effort of remarkable scale. Hundreds of thousands of people contribute directly or indirectly. Factories manufacture components. Universities conduct research. Government agencies coordinate planning and testing. Vast amounts of data move between laboratories, offices, and industrial facilities. The challenge extends beyond building a spacecraft. Every stage of a mission must function correctly. Astronauts must survive launch, travel through space, navigate accurately, enter lunar orbit, descend safely, return from the lunar surface, and come home to Earth. Each requirement introduces additional complexity. Engineers divide large problems into smaller tasks. Specialists focus on propulsion, guidance, communications materials, medicine, computing, and many other fields. Computers of the era possess far less processing power than machines common many decades later. Nevertheless, they represent advanced technology for their time. Engineers use them to perform calculations, simulate missions, and assist navigation. Reliability becomes more important than speed. Systems must operate predictably under demanding conditions. Public interest remains high throughout the program. Large audiences watch launches and follow mission reports. Schools discuss developments in space exploration. Scientific achievements become part of everyday conversation. For many people, lunar exploration represents curiosity, discovery, and technical progress. For others, it reflects national goals and international competition. Different perspectives exist, yet attention remains widespread. The astronauts themselves are only the most visible participants in a much larger undertaking. Behind every mission stands a network of controllers, engineers, technicians, medical personnel, researchers, and support staff. Their work often occurs far from cameras and public events. Countless tests take place before any spacecraft leaves the ground. Equipment is inspected repeatedly. Procedures are reviewed and revised. Unexpected problems are investigated carefully. Scientific understanding of the Moon continues to improve as the launch date approaches. Observations indicate a solid surface capable of supporting landing vehicles. Measurements provide better estimates of terrain characteristics. Nevertheless, uncertainties remain. Scientists understand many aspects of the lunar environment, but some details can only be confirmed through direct human exploration. Observations indicate likely conditions. It remains uncertain whether every prediction accurately reflects the reality awaiting visitors on the surface. By the summer of 1969, Earth has become the center of an enormous effort aimed at a single destination visible in the night sky. Cities continue their ordinary routines. Oceans continue their tides. Seasons continue their cycles. Yet within laboratories, factories, offices, and launch facilities, preparations approach their final stages. The planet remains the home from which the mission begins, the source of all technology involved, and the place to which every traveler intends to return. Apollo 11 exists first as an achievement of Earth itself, created by people working beneath its atmosphere, while looking outward toward the Moon. The Saturn V stands among the largest and most powerful machines ever built by human beings. Before Apollo 11 leaves Earth, this immense launch vehicle occupies a central place in the effort to reach the Moon. Rising above the flat landscape of the launch complex, it appears less like a conventional aircraft and more like a vertical structure assembled from fuel tanks, engines, pipes, electrical systems, and carefully engineered materials. Every part exists for a specific purpose. Every component contributes to a sequence of events that must unfold with extraordinary precision. The rocket begins as a design challenge. Engineers understand that sending humans to the Moon requires far more energy than placing a spacecraft into orbit around Earth. A lunar mission demands enough power to lift a spacecraft from the surface, accelerate it beyond low orbit, guide it toward the Moon, and support a safe return journey. The required mass includes astronauts' life support equipment, navigation systems, fuel, scientific instruments, and protective structures. The result is a vehicle of unprecedented scale. From a distance, the Saturn V appears simple. Its shape resembles a tall cylinder narrowing toward the top. Closer examination reveals a complex arrangement of stages. A stage is a major section of a rocket containing engines, fuel, and supporting systems. After completing its task, a stage separates from the vehicle, allowing the remaining spacecraft to continue with less mass. This approach improves efficiency and makes lunar travel possible with the technology available during the 1960s. The lower stage is the largest. It contains enormous tanks filled with refined kerosene and liquid oxygen. Liquid oxygen is oxygen cooled until it becomes a very cold liquid. Together, these substances provide fuel for 5 giant engines mounted beneath the rocket. Each engine is a remarkable machine in its own right. Pumps move fuel and oxidizer into combustion chambers at high pressure. Burning propellants create hot gases that rush through nozzles and generate thrust. Thrust is the force that pushes the rocket upward against Earth's gravity. The engines must operate under extreme conditions. Temperatures inside combustion chambers reach levels capable of damaging many materials. Vibrations travel through the structure during operation. Fuel flows at tremendous rates. Engineers spend years testing engine designs, examining failures, and refining components. Reliability becomes essential because a malfunction during launch could end the mission within moments. Above the first stage sits the second stage. This section uses liquid hydrogen and liquid oxygen as propellants. Liquid hydrogen is exceptionally light and must be stored at very low temperatures. Handling such materials requires careful insulation and specialized equipment. Engineers develop methods for maintaining stable conditions despite the heat of the surrounding environment. The second stage continues accelerating the spacecraft after the first stage completes its work and separates. Higher still is the third stage. Although smaller than the stages beneath it, it performs one of the mission's most important tasks. After reaching Earth orbit, this stage later provides the additional acceleration needed to send Apollo 11 toward the Moon. Its engines must restart in space after a period of coasting, demonstrating a capability essential for lunar travel. This requirement introduces additional complexity into the design and testing process. At the top of the rocket sits the spacecraft itself. The Command Module, Service Module, and Lunar Module are protected beneath a streamlined structure during launch. Together they form the payload carried by the Saturn V. Although public attention often focuses on the astronauts, the rocket serves as the indispensable foundation of the mission. Without its power, no lunar journey can begin. Constructing a Saturn V requires contributions from many organizations across the United States. Components are manufactured in different locations and transported over long distances. Some sections travel by specially designed barges because their size exceeds the limits of many roads and railways. Coordination becomes a major undertaking. Engineers must ensure that parts produced hundreds or thousands of kilometers apart fit together precisely when assembled. Materials receive careful attention throughout the process. Designers seek combinations of strength and low mass. Every kilogram added to the vehicle reduces efficiency. Yet structures must withstand enormous forces during launch. Thin metal walls support tanks holding vast quantities of propellant. Internal frameworks distribute loads through the rocket. Specialized alloys provide strength while limiting weight. Testing occupies a significant portion of the development effort. Individual components undergo examination before being integrated into larger systems. Engines are fired repeatedly on test stands. Tanks are pressurized. Electronics are evaluated under simulated operating conditions. Engineers intentionally expose equipment to stresses expected during flight. Problems discovered during testing can often be corrected before launch, improving overall reliability. The launch vehicle also contains guidance systems. These systems monitor the rocket's position, orientation, and movement. Computers process information from instruments and help direct the vehicle along its planned path. During ascent, the rocket must remain stable while accelerating through the atmosphere and into space. Small adjustments made by engines and control systems keep the vehicle aligned with mission requirements. Safety considerations influence every stage of development. Engineers recognize that human lives depend upon the performance of the rocket. Redundant systems are incorporated where practical. A redundant system provides backup capability if a primary component fails. Inspections occur repeatedly. Procedures are documented carefully. Technical reviews examine designs in detail. Large teams evaluate potential risks and seek ways to reduce them. The completed Saturn V possesses a scale difficult to appreciate fully from photographs alone. Standing near the vehicle reveals its immense height and volume. Fuel tanks large enough to contain substantial buildings occupy much of its structure. Yet despite its size, the rocket represents a balance between strength and efficiency. It is neither excessively heavy nor unnecessarily complex. Every major feature reflects a specific engineering requirement. By the time Apollo 11 approaches its launch date, the Saturn V is no longer merely a design or an experimental project. Earlier missions have demonstrated its capabilities, providing valuable experience and confidence. Engineers continue examining data and refining procedures, but the vehicle has proven capable of carrying humans beyond Earth orbit. The giant rocket waits on the launch pad as the product of years of planning, testing, manufacturing, and scientific understanding. It stands motionless beneath the sky filled with technology created on Earth and prepared to transform stored chemical energy into a journey toward the moon. The astronauts selected for Apollo 11 spend years preparing for a mission unlike any previously attempted. Before they enter the spacecraft, before the engines ignite, and before the journey toward the moon begins, their daily lives become structured around training, study, testing, and repetition. The mission depends upon machinery of remarkable complexity, yet it also depends upon the ability of human beings to operate that machinery correctly under demanding conditions. Preparation, therefore, becomes a process extending far beyond physical fitness. It includes technical knowledge, procedural discipline, teamwork, and the development of calm judgment. The 3 members of the Apollo 11 crew each arrive with substantial experience. Neil Armstrong serves as mission commander. Edwin Aldrin serves as lunar module pilot. Michael Collins serves as command module pilot. All 3 possess backgrounds connected to aviation and military service. They have accumulated extensive experience operating sophisticated aircraft and working within structured technical environments. Their previous careers provide a foundation, but a lunar mission requires additional preparation far beyond ordinary flight training. Training begins long before the specific crew assignment. Astronaut candidates study engineering principles, spacecraft systems, orbital mechanics, geology, communications procedures, navigation methods, and emergency operations. Orbital mechanics is the science describing how objects move under the influence of gravity. Understanding these principles helps astronauts interpret mission plans and respond effectively if unexpected situations arise. Classroom instruction occupies a significant portion of preparation. Engineers and specialists explain the design and operation of spacecraft components. Astronauts learn how electrical systems function, how environmental controls regulate cabin conditions, how communications equipment transmits information, and how propulsion systems perform critical maneuvers. The goal is not merely familiarity. Crew members must understand their equipment thoroughly enough to recognize irregularities and respond appropriately. Simulation becomes one of the most important tools in astronaut training. Simulators are specialized devices designed to recreate conditions expected during a mission. Some reproduce spacecraft interiors with remarkable accuracy. Switches displays instruments and controls are arranged exactly as they appear in the actual vehicle. Astronauts repeatedly practice normal operations as well as emergency scenarios. Instructors introduce unexpected problems to test reactions and decision-making. Through repetition, procedures become familiar and efficient. Many training sessions involve situations that never occur during the actual mission. Nevertheless, preparing for unlikely events remains essential. Engineers understand that spaceflight involves risks. Equipment failures, communication interruptions, navigation challenges and other complications must be considered. Astronauts therefore rehearse a wide range of possibilities. The purpose is not to predict every event, but to develop confidence and competence under pressure. The lunar module receives special attention. No aircraft on Earth behaves exactly like a spacecraft descending toward the Moon. The lunar environment lacks a substantial atmosphere. Traditional aerodynamic flight is therefore impossible. To help prepare for landing operations, NASA develops specialized training vehicles capable of approximating some aspects of lunar descent. These machines allow astronauts to practice controlling thrust and maintaining stability while descending toward the ground. Such training carries its own risks. During one exercise in a lunar landing training vehicle, Armstrong experiences a serious malfunction. The machine becomes unstable, forcing him to eject shortly before it crashes. He survives without significant injury and continues training. The incident illustrates the demanding nature of preparation and the challenges associated with developing entirely new methods of flight. Physical conditioning also forms part of the process. Astronauts must remain healthy throughout the mission. Medical examinations occur regularly. Doctors monitor cardiovascular, health, vision, hearing, and other important factors. Although spaceflight is not primarily a test of athletic performance, physical fitness contributes to overall readiness and resilience. The crew also spends considerable time working together. Apollo 11 is not an individual undertaking. Success depends upon coordination among all three astronauts. Each crew member holds specific responsibilities, yet the mission requires constant cooperation. Training exercises reinforce communication habits and shared understanding. Team members learn not only their own tasks, but also the duties of their colleagues. Spacesuits represent another major area of preparation. These garments function as miniature life support systems. On the Moon, astronauts cannot rely on a breathable atmosphere or moderate temperatures. The suits provide oxygen, remove carbon dioxide, regulate temperature, and offer protection from the harsh environment. Learning to operate while wearing them requires practice, because movement becomes more difficult than under ordinary conditions. Astronauts spend many hours performing tasks while suited. They practice walking, handling equipment, collecting samples, and operating tools. Even simple activities can become challenging when gloves reduce dexterity and pressurized garments resist movement. Repetition helps identify efficient techniques and reveals potential difficulties before the mission begins. Geology training occupies an important place in preparation for lunar exploration. Scientists hope that astronauts will return valuable rock and soil samples from the Moon. To improve their observational skills, crew members visit geological sites on Earth. Specialists teach them how to recognize significant features and document observations effectively. Although the Moon differs from Earth in many ways, experience examining rocks and landforms helps prepare astronauts for scientific work on the surface. Navigation training extends beyond operating instruments. Astronauts learn the logic behind mission trajectories and maneuver planning. They study star sightings used for orientation and become familiar with procedures for verifying spacecraft position. Computers assist navigation, but human understanding remains important. Crew members must be capable of monitoring systems and identifying possible discrepancies. A large portion of preparation involves interaction with mission control. The flight controllers on Earth and the astronauts in space function as parts of a single operational team. Communications procedures are therefore practiced repeatedly. Messages are designed to be clear, concise, and precise. Consistency reduces confusion and helps ensure efficient operations during critical phases of the mission. As launch approaches, training intensifies. Simulations become increasingly detailed. Final reviews examine mission objectives and procedures. Equipment configurations are verified. Medical evaluations continue. Every aspect of the mission receives careful attention. The astronauts remain aware that they are preparing for a journey no human has previously completed. By the final weeks before Apollo 11, preparation has transformed many mission tasks into familiar routines. The spacecraft remains complex. The challenges remain substantial. Yet years of study, practice, testing, and teamwork have created a foundation upon which the mission can proceed. The crew enters the final phase not as explorers relying on improvisation, but as highly trained professionals shaped by thousands of hours of preparation. Their readiness reflects the combined efforts of instructors, engineers, scientists, physicians, and support personnel who have worked steadily toward a single objective. The mission still awaits launch, but the human element has been prepared as thoroughly as possible beneath the atmosphere of Earth. Launch day arrives after years of planning, testing, construction, and preparation. At the edge of the Atlantic coast in Florida, the Apollo 11 mission enters the final stage before departure from Earth. The launch complex stands within a landscape shaped by flat terrain, open sky, coastal vegetation, and the nearby ocean. Long before sunrise activity begins across the facilities supporting the mission, engineers, technicians, controllers, medical personnel, and support teams move through carefully organized procedures developed over many years of experience. The launch site itself is the product of practical considerations. Rockets of great size require large safety zones and access to broad downrange areas over water. The eastern coast of Florida provides both advantages. A vehicle launched eastward gains a small benefit from Earth's rotation, and flight paths can extend over the Atlantic Ocean rather than heavily populated regions. These geographical factors contribute to the selection of the location that becomes one of the most recognized launch centers in history. The Saturn V dominates the landscape. Standing upright on the launch pad, it appears almost motionless against the sky. Yet beneath its quiet exterior lies an immense concentration of stored energy. Tanks contain hundreds of thousands of kilograms of propellants. Electrical systems remain active. Monitoring equipment continuously evaluates the condition of countless components. The rocket waits, but it is not inactive. Engineers observe a constant flow of information from sensors distributed throughout the vehicle. Weather receives careful attention during the final hours before launch. Conditions in the atmosphere can influence both safety and mission success. Specialists evaluate wind speed, cloud cover, precipitation visibility, and the possibility of electrical activity. Rockets travel through different layers of the atmosphere during ascent, and strong winds at altitude can affect structural loads. Lightning poses additional risks. Meteorologists provide detailed assessments so that launch managers can make informed decisions. The atmosphere surrounding Earth appears calm from the ground on many days, but it contains complex patterns of motion extending through different heights. Weather balloons and radar systems help characterize these conditions. Data collected before launch contributes to planning and allows engineers to verify that environmental conditions remain within acceptable limits. As the scheduled launch time approaches, the astronauts begin their own carefully structured sequence of activities. Medical evaluations confirm their readiness. Specialized garments are worn beneath pressure suits. Technicians assist with final preparations and equipment checks. Every step follows procedures refined through previous missions. The objective is consistency, reducing the likelihood of errors during a period when attention naturally focuses on the approaching launch. Transportation carries the crew toward the launch complex. Along the route, workers and observers understand that years of effort now converge upon a single event. Yet the atmosphere within operational teams remains professional rather than ceremonial. Countless technical tasks still require completion. Systems must continue functioning correctly until the moment of liftoff. The astronauts enter the spacecraft through an access structure connected to the upper portion of the Saturn V. Once inside, they settle into positions designed for launch. The cabin environment undergoes final verification. Communications links are tested. Instruments display information about vehicle status. Although the crew occupies a relatively small volume near the top of the rocket, they remain connected through communication networks to an extensive support organization spread across the launch center. Meanwhile, fueling operations represent one of the most demanding aspects of launch preparation. Certain propellants must be loaded relatively close to launch because of their extremely low temperatures. Liquid oxygen and liquid hydrogen require careful handling. Engineers monitor temperatures, pressures, flow rates, and tank levels continuously. Specialized equipment compensates for evaporation and thermal changes. The process reflects decades of experience in cryogenic engineering, the management of very cold materials. Inside control rooms, teams monitor displays presenting information from thousands of sensors. Each group focuses on specific systems. Propulsion specialists examine engine parameters. Electrical engineers observe power systems. Guidance experts verify navigation equipment. Communications personnel evaluate signal quality. Flight directors coordinate the overall process. Every participant contributes to a broader effort aimed at ensuring readiness for launch. The countdown serves as a structured framework for these activities. Contrary to popular perception, the countdown is not merely a clock moving steadily towards zero. It contains planned pauses allowing teams to review progress and resolve issues. During these periods, managers evaluate data and confirm that critical requirements have been satisfied. If necessary, the countdown can be delayed while problems are investigated. As launch time approaches, the pace of activity increases. Final checks occur across all major systems. The launch escape system remains armed and ready. This emergency rocket is designed to pull the crew capsule away from danger if a severe problem develops during certain phases of ascent. Its presence reflects the emphasis placed on crew safety, despite the inherent risks of spaceflight. The surrounding region attracts large numbers of observers. Many gather along coastlines and viewing areas to witness the event. Television networks prepare broadcasts. Newspapers assign reporters. Around the world, audiences follow developments through various forms of media. Yet despite widespread public attention, operational decisions continue to depend entirely upon technical considerations rather than public expectations. During the final minutes, automatic systems assume increasing responsibility for launch operations. Computers monitor critical functions and execute sequences requiring precise timing. Human operators remain ready to intervene if necessary, but automation helps ensure consistency. Valves open and close. Pressures adjust. Guidance systems transition toward flight mode. The vehicle gradually shifts from preparation to readiness. At the designated moment, ignition begins beneath the first stage. The 5 engines do not reach full power instantly. Instead, thrust builds over a brief interval while monitoring systems verify proper operation. The rocket remains secured temporarily as engineers confirm that engine performance falls within acceptable limits. Only after these checks does release occur. Flames and exhaust emerge beneath the vehicle. Tremendous quantities of hot gas rush downward. The launch structure channels this flow away from the rocket. For a brief period, the Saturn V appears almost suspended above the pad as thrust overcomes gravity. Then the vehicle begins moving upward. The motion is initially slow. The rocket possesses enormous mass, and acceleration develops gradually. As propellant is consumed, the vehicle becomes lighter and climbs more rapidly. The ascent marks the moment when Apollo 11 finally departs the surface of Earth. From the perspective of those watching below, the giant rocket rises into the atmosphere, carrying the spacecraft and crew towards space. Years of preparation culminate in this departure. The launch site remains behind on the coast, while the vehicle continues upward through the air above the planet that created it. Earth still surrounds the mission on every side, but the journey has begun. As the Saturn V climbs away from the launch site, Apollo 11 remains within Earth's immediate surroundings. The spacecraft has left the ground, but it has not yet departed the region dominated by the planet's gravity and operational control. During this phase of the mission, attention focuses on reaching orbit safely and preparing the spacecraft for the tasks ahead. The environment outside changes rapidly, yet Earth remains the central reference point for every action. The ascent through the atmosphere continues for only a relatively short period compared with the overall journey, but it represents one of the most demanding portions of the mission. The rocket accelerates steadily while passing through layers of air that vary in density and temperature. Engineers have carefully designed the flight path to balance efficiency and structural safety. Excessive aerodynamic forces could damage the vehicle, while insufficient acceleration could prevent the mission from reaching orbit. As altitude increases, the atmosphere grows progressively thinner. Air resistance decreases. The brilliant plume beneath the rocket expands differently as external pressure falls. Inside the spacecraft, the astronauts monitor instruments and maintain communication with flight controllers on Earth. Most operations proceed according to plans established long before launch day, but constant observation remains necessary. The first stage performs its task for only a few minutes. During this brief interval, it consumes enormous quantities of fuel and liquid oxygen. The 5 engines generate the thrust needed to lift the rocket away from Earth and establish the early portion of the ascent. Once the propellants are exhausted, the stage has completed its purpose. Separation mechanisms activate and the empty structure falls away. Stage separation is a carefully engineered process. Explosive devices and mechanical systems ensure that the spent stage moves safely away from the rest of the vehicle. Almost immediately, the engines of the second stage ignite. The transition occurs high above the surface, where the atmosphere is already much thinner than at sea level. The second stage continues accelerating Apollo 11 toward orbital speed. Reaching orbit requires more than simply climbing upward. A spacecraft must also move sideways at tremendous velocity. Orbit is a state of continuous free fall around Earth. A spacecraft travels forward so quickly that as it falls toward the planet, the surface curves away beneath it. The result is a continuous path around the world. Within the spacecraft, the crew experiences conditions unlike those of ordinary flight. Vibrations gradually change as different stages operate. Acceleration levels vary throughout the ascent. The astronauts remain secured in their seats, monitoring systems and responding to procedures when required. Although much of the launch sequence is automated, human supervision remains important. The second stage eventually completes its work and separates. The third stage then assumes responsibility for the final portion of the climb into Earth orbit. Its engine provides additional acceleration, refining the trajectory and bringing the spacecraft to the conditions necessary for orbital flight. At engine shutdown, a significant transition occurs. The spacecraft is no longer a vehicle struggling upward through the atmosphere. It has become an object circling Earth. The sensation of sustained acceleration disappears. The crew enters a condition commonly called weightlessness. In physical terms, the astronauts and spacecraft are falling together around the planet, producing the experience of apparent weightlessness inside the cabin. Earth now appears very different from the view available at the launch site. Through spacecraft windows, large portions of the planet become visible at once. Oceans, cloud systems, coastlines, and landforms stretch across vast distances. The atmosphere appears as a thin layer surrounding the globe. From orbit, the protective envelope of air that supports life reveals its relative fragility. Compared with the size of Earth, the atmosphere is remarkably thin. Apollo 11 does not immediately leave for the Moon upon reaching orbit. Instead, the mission enters a planned period of evaluation and preparation. Flight controllers and astronauts examine spacecraft performance carefully. Systems are checked to confirm that they function correctly after launch. Engineers on the ground review data transmitted from the vehicle. Any significant problem discovered during this phase could influence decisions about proceeding with the mission. The orbit itself serves practical purposes. It provides time to verify readiness before committing to the longer journey beyond Earth. Once a spacecraft departs for the Moon, returning quickly becomes far more difficult. Mission planners therefore use Earth orbit as an opportunity to assess vehicle health and operational status. The astronauts continue monitoring guidance systems, communications equipment, environmental controls, and electrical power. Environmental controls regulate cabin temperature, pressure, humidity, and air composition. These systems are essential because the spacecraft must provide a stable living environment independent of external conditions. Meanwhile, the third stage remains attached to the spacecraft. Although its initial task is complete, it still contains propellant reserved for a later maneuver. The stage and spacecraft circle Earth together while preparations continue. Controllers analyze tracking information from stations distributed around the globe. These facilities help determine the vehicle's position and verify that the orbit matches mission requirements. Communications networks play a critical role throughout this period. Radio signals connect the astronauts with mission control. Engineers receive continuous streams of information concerning temperatures, pressures, voltages, fuel quantities, and countless other measurements. The mission depends upon this flow of data. Decisions made on Earth rely upon accurate knowledge of spacecraft conditions. Inside the cabin, daily life begins to adjust to orbital conditions. Objects no longer remain where they are placed unless secured. Small items can drift through the cabin. Movement requires gentle pushes rather than ordinary walking. The astronauts, already familiar with weightlessness from previous spaceflight experience, adapt efficiently to the environment. The view outside remains one of the most striking aspects of orbital flight. Cloud formations reveal patterns invisible from the ground. Sunlight reflects from oceans. Weather systems extend across entire regions. Day and night alternate rapidly as the spacecraft circles the planet. Yet despite the beauty of these scenes, operational responsibilities remain the primary focus. By the end of this phase, Apollo 11 has successfully achieved orbit and demonstrated that its major systems are functioning as expected. The spacecraft remains firmly within Earth's gravitational influence, circling the planet that launched it only a short time earlier. The mission has advanced from the launch pad into space, but Earth still dominates the environment. Oceans, continents, atmosphere tracking stations, communication networks, and mission controllers continue shaping every aspect of operations. The spacecraft moves swiftly above the world, completing orbit after orbit, while preparations continue within the familiar reach of home. Apollo 11 remains in Earth orbit only long enough to confirm that the spacecraft and its crew are ready for the next stage of the mission. Once engineers and flight controllers complete their evaluations, attention turns to the maneuver that will carry the astronauts beyond the immediate surroundings of their home planet. This event marks the transition from orbital flight around Earth to travel through the region between Earth and the Moon, a vast expanse often called cislunar space. The spacecraft continues circling Earth while preparations proceed. Guidance systems calculate the precise moment when the third stage must ignite again. Timing is critical. The Moon is not a stationary target. It moves continuously along its orbit around Earth. Apollo 11 must therefore depart at exactly the right time and in exactly the right direction to arrive where the Moon will be several days later. At the planned moment, the engine of the third stage ignites once more. This maneuver is known as translunar injection. The purpose is simple in principle, but demanding in execution. The spacecraft must increase its speed enough to escape its temporary orbit around Earth and enter a trajectory leading toward the Moon. For several minutes, the engine operates steadily. Acceleration presses the astronauts gently into their seats. When the burn ends, Apollo 11 is no longer merely orbiting Earth. It is traveling outward into space between the two worlds. Earth's gravity continues to influence the spacecraft, but the vehicle is now committed to a new path extending hundreds of thousands of kilometers from the planet. Soon afterward, another important operation begins. The command module separates from the third stage and performs a carefully planned maneuver. It turns around in space, approaches the lunar module stored within the upper section of the stage, and docks with it. Docking is the process by which two spacecraft connect mechanically and electrically. Once the connection is secure, the combined spacecraft separates from the third stage and continues independently. This sequence requires precision. Although motion in space often appears slow, the operation involves careful control of position and orientation. Small thruster firings adjust movement. The astronauts monitor instruments and visual references while carrying out procedures practiced repeatedly during training. Successful docking transforms separate components into the configuration required for the lunar mission. With the maneuver complete, the third stage has fulfilled its purpose. It drifts away while Apollo 11 continues its journey. The spacecraft now consists primarily of the command module, the service module, and the lunar module. Together they form the vehicle that will carry the crew toward the Moon and eventually return them to Earth. As distance from Earth increases, the appearance of the planet gradually changes. At first, Earth still dominates the view through spacecraft windows. Continents, oceans, and cloud systems remain visible in remarkable detail. Over time, however, the planet begins to shrink. The familiar features of the surface become less distinct. The globe increasingly resembles a complete sphere suspended against the darkness of space. The environment outside differs greatly from conditions experienced near Earth's surface. There is no atmosphere through which sunlight can scatter. The sky appears dark even when the sun shines brightly. Temperature conditions depend heavily upon exposure to sunlight and shadow. The spacecraft relies entirely upon its own systems for life support power, generation, navigation, and communication. Inside the vehicle, daily operations follow carefully planned schedules. The astronauts perform system checks, conduct observations, maintain communications with Earth, and prepare for future mission phases. Although the spacecraft travels at tremendous speed, the experience often appears calm from within the cabin. Space provides few visual references for judging motion. Without nearby objects passing by, rapid travel can seem almost motionless. Navigation remains a constant responsibility. Computers assist with calculations, but astronauts and controllers verify information through multiple methods. One important technique involves observing stars. Because stars occupy predictable positions, they provide useful reference points for determining spacecraft orientation. Optical instruments help the crew make these observations and compare them with expected values. Communication delays begin to increase slightly as the spacecraft moves farther from Earth. Radio signals travel at the speed of light, which is extremely fast, yet the growing distance introduces measurable intervals between transmission and reception. The delays remain short, but they remind everyone involved that the spacecraft is steadily leaving its home planet behind. Earth itself becomes an object of observation. From this distance, weather systems reveal large-scale structures impossible to appreciate fully from the ground. White cloud formations swirl across oceans and continents. The atmosphere appears as a delicate layer surrounding the globe. The visual impression reinforces scientific understanding developed over many decades. Life exists within a comparatively thin region, protected by air, water, and planetary conditions suitable for living organisms. The astronauts also adapt to the rhythms of long-duration space travel. Eating, sleeping, hygiene, and routine maintenance all require procedures different from those used on Earth. Weightlessness influences nearly every activity. Food must be managed carefully. Equipment must be secured. Movement through the cabin relies upon handholds and gentle pushes rather than ordinary walking. Mission control remains deeply involved throughout the journey. Teams on Earth monitor spacecraft performance continuously. Telemetry data provides information about temperatures, electrical systems, fuel supplies, and many other operational parameters. Telemetry is the automatic transmission of measurements from a distant vehicle to observers elsewhere. This flow of information allows specialists to evaluate spacecraft health and recommend actions if necessary. As Apollo 11 travels farther outward, the balance of gravitational influence gradually changes. Earth remains the dominant force for much of the journey, but the Moon's gravity becomes increasingly significant. The spacecraft follows a carefully calculated path shaped by both bodies. Corrections are occasionally performed using small rocket engines. These maneuvers are typically modest because navigation planning has been highly accurate. The voyage through cislunar space reveals the scale of the Earth-Moon system. From the ground, the Moon often appears close and familiar. In reality, the distance separating the two worlds is immense. Hours pass, then days. The spacecraft continues steadily across the intervening region. Earth grows smaller behind it, while the Moon slowly becomes more prominent ahead. By the end of this stage, Apollo 11 exists in a realm occupied by neither Earth nor Moon alone. It travels through the broad expanse connecting the two bodies, supported entirely by the systems carried aboard the spacecraft and guided by calculations made on Earth. The astronauts live and work within a small vehicle moving through a largely empty environment. crossing a distance that no human travelers had previously crossed, with the intention of landing on another world. After several days of travel through cislunar space, the Moon gradually changes from a distant destination into a nearby world. Apollo 11 continues along its planned trajectory, while the appearance of the lunar surface becomes increasingly detailed through the spacecraft windows. Features that once seemed subtle and indistinct begin to reveal structure. Large dark plains contrast with brighter highland regions. Circular impact craters become easier to distinguish. Mountains and ridges cast shadows that emphasize the rugged nature of the terrain. The Moon differs greatly from Earth. It possesses no substantial atmosphere, no oceans, and no active weather systems comparable to those shaping conditions on Earth. Its surface preserves evidence of events that occurred across immense spans of time. Impact craters remain visible because there is little wind or flowing water to erode them. Geological processes operate very differently from those familiar on Earth's surface. As Apollo 11 approaches the Moon, navigation becomes increasingly important. The spacecraft is not simply flying toward the lunar surface. Its first objective is to enter orbit around the Moon. Achieving this requires a carefully timed engine burn. Without that maneuver, the spacecraft would continue along its path and pass beyond the Moon rather than becoming captured into orbit. Mission planners have calculated the required trajectory long before launch. Nevertheless, observations and measurements continue throughout the approach. Tracking data from Earth combines with information gathered aboard the spacecraft. Engineers and astronauts verify that Apollo 11 remains where it is expected to be. Small corrections performed earlier in the journey contribute to the accuracy of this arrival. The Moon's gravity gradually exerts a stronger influence on the spacecraft. Earth still affects the trajectory, but the balance changes as Apollo 11 moves deeper into the lunar environment. The Moon is much less massive than Earth, yet its gravitational pull is entirely sufficient to guide spacecraft into orbit when approached correctly. From the crew's perspective, the Moon begins to fill a larger portion of the visible scene. Surface features become more recognizable. Vast impact basins stretch across hundreds of kilometers. Bright rays radiate outward from certain craters. The contrast between illuminated and shadowed terrain creates dramatic patterns. Yet despite these visual impressions, the astronauts remain focused on operational tasks. Observation supports navigation, but precision remains essential. As arrival approaches, Apollo 11 passes behind the Moon relative to Earth. This event has important consequences for communication. The bulk of the Moon blocks radio signals traveling directly between the spacecraft and Earth. For a period of time, mission control cannot communicate with the crew. This temporary loss of contact is expected and fully understood. It results from geometry rather than technical failure. While hidden from direct communication, the spacecraft prepares for one of the most significant maneuvers of the mission. The service module engine must fire at precisely the correct moment to slow the spacecraft relative to the Moon. This reduction in velocity allows lunar gravity to capture Apollo 11 into orbit. Inside the spacecraft, instruments provide critical information. Guidance systems determine position and velocity. Computers assist with calculations. The astronauts monitor performance and verify procedures. Years of engineering and preparation converge upon this operation. At the designated time, the engine ignites. The burn occurs while the spacecraft remains beyond direct radio contact with Earth. Mission control cannot observe the maneuver in real time. Engineers must wait until Apollo 11 reappears from behind the Moon to confirm success. The engine firing changes the spacecraft's trajectory significantly. Before the maneuver, Apollo 11 follows a path carrying it past the Moon. Afterward, it enters an elongated lunar orbit. The spacecraft has become a temporary satellite of the Moon, rather than a traveler merely passing nearby. Eventually, Apollo 11 emerges from the far side of the Moon, and communication resumes. Signals once again travel between the spacecraft and Earth. Data confirms that the maneuver has succeeded. The crew now circles the Moon. The view from lunar orbit differs profoundly from anything visible on Earth. The surface stretches beneath the spacecraft without atmospheric haze. Craters of many sizes cover the landscape. Some overlap older structures, recording a long history of impacts. Large plains formed by ancient volcanic activity appear darker than surrounding regions. Mountain ranges rise along the edges of enormous impact basins created billions of years earlier. One of the most striking characteristics of the Moon is the sharpness of visual detail. Without a substantial atmosphere to scatter light, boundaries between illuminated and shadowed areas appear unusually distinct. Shadows can become very dark. Sunlit regions can appear intensely bright. This lighting environment presents challenges for observation and photography, requiring careful attention from astronauts and engineers. The far side of the Moon attracts particular interest. This hemisphere cannot be observed directly from Earth, because the Moon rotates in such a way that the same face generally remains oriented toward our planet. Earlier robotic missions have photographed the far side, but direct human observation from orbit provides additional perspective. The terrain differs noticeably from much of the near side, containing extensive highland regions and comparatively fewer large dark plains. Apollo 11 continues circling the Moon while preparations for later operations proceed. Each orbit provides opportunities to observe surface features and verify navigation data. The spacecraft passes alternately through sunlight and shadow. Temperature conditions outside vary dramatically between illuminated and dark regions. Internal systems maintain stable conditions for the crew despite these external extremes. The Moon itself reveals evidence of its ancient history. Scientists interpret many visible features as the result of impacts from asteroids and other objects during the early history of the solar system. Observations indicate that volcanic activity also influenced parts of the surface long ago. By the time of Apollo 11, however, the Moon appears geologically quiet compared with Earth. No active weather reshapes the landscape. No oceans alter coastlines. The surface preserves records extending far into the past. As Apollo 11 continues its path around the Moon, the destination of the mission becomes increasingly real. The lunar world is no longer an object viewed from Earth or a target represented on charts. It surrounds the spacecraft directly. Craters, plains, ridges, and mountains pass beneath each orbit. The crew now operates within the immediate environment of another celestial body, moving through a region where lunar gravity governs their motion, and where every observation brings greater familiarity with the world they have travelled so far to reach. Apollo 11 now moves repeatedly around the Moon, completing orbit after orbit, above a landscape that remains unchanged by weather, vegetation, or flowing water. The spacecraft exists entirely within the lunar environment. Earth is still visible at certain times through the windows, appearing as a distant globe suspended in darkness. But daily operations are now centered on the Moon below. Every circuit around the lunar surface provides new opportunities to observe terrain, refine navigation, and prepare for the activities that will follow. The orbit itself is carefully planned. Apollo 11 does not simply circle the Moon at a random altitude. Engineers calculate a path that balances safety, fuel efficiency, communication requirements, and mission objectives. The spacecraft follows a predictable trajectory shaped by lunar gravity and the velocity established during earlier maneuvers. Maintaining this orbit requires continuous awareness of position and motion. From the perspective of the crew, the lunar surface passes silently beneath the spacecraft. Large craters appear, drift across view, and disappear beyond the horizon. Mountain ranges cast long shadows. broad dark plains contrast with brighter highland regions. Without an atmosphere to soften distant features, the landscape often appears unusually sharp and clear. One of the primary tasks during this phase involves detailed observation of the intended landing region. Although robotic missions and earlier Apollo flights have gathered extensive information, direct examination from orbit provides an additional layer of confidence. Astronauts compare visible landmarks with maps and photographs. Surface features help verify that navigation calculations remain accurate. The planned landing site lies within a broad plain known as the Sea of Tranquility. Despite its name, this region contains no water. The term originates from historical naming conventions established centuries before the true nature of the Moon was understood. The area is actually a basaltic plain formed long ago when molten rock spread across portions of the lunar surface and later solidified. As Apollo 11 passes over different regions, the astronauts gain a growing appreciation for the scale of lunar geography. Some craters extend across tens of kilometers, others are far larger. Impact basins hundreds of kilometers wide reveal evidence of ancient collisions that helped shape the Moon's appearance. The surface reflects billions of years of accumulated history preserved in rock and dust. The spacecraft itself requires continuous attention. While orbital flight may appear routine compared with launch or lunar landing, many important systems remain active. Electrical power must be managed carefully. Environmental controls maintain cabin conditions. Communications equipment transmits information to Earth. Guidance systems track the spacecraft's position and orientation. The command module serves as the primary living and operational space for the crew during this stage. Its interior remains compact. Every item has been positioned deliberately. Storage areas contain supplies, equipment, and documentation required for the mission. Weightlessness continues to influence daily activities. Objects remain secured whenever possible to prevent drifting through the cabin. Michael Collins assumes particular responsibility for many orbital operations. As command module pilot, he monitors systems and prepares for future phases of the mission. His role requires detailed knowledge of navigation communications and spacecraft performance. Although public attention later focuses heavily on the lunar landing itself, orbital operations demand equal professionalism and concentration. Meanwhile, Neil Armstrong and Edwin Aldrin begin concentrating increasingly on the lunar module. This vehicle will eventually separate from the command module and carry them toward the surface. During orbital periods, they review procedures, inspect equipment, and verify readiness. The lunar module represents a specialized spacecraft designed exclusively for operation in the lunar environment. The design of the lunar module reflects the absence of an atmosphere on the Moon. Unlike aircraft, it requires no aerodynamic shape. Engineers focus instead on efficiency, visibility, and the ability to land and depart using rocket propulsion alone. Its appearance differs significantly from conventional flying vehicles because it is intended to function entirely in space and on the lunar surface. Mission control remains deeply involved in every stage of orbital operations. Tracking stations on Earth receive data from Apollo 11 and transmit instructions when necessary. Specialists analyze information concerning fuel supplies, system performance, and navigational accuracy. The relationship between the spacecraft and the ground teams remains continuous despite the great distance separating them. The Moon itself introduces unique navigational considerations. Unlike Earth, its gravitational field is not perfectly uniform. Variations in mass distribution beneath the surface create subtle differences in gravitational strength across certain regions. Scientists understand some aspects of these variations through observations from earlier missions. Flight planners account for their effects when designing lunar orbits. During each orbit, lighting conditions change according to position relative to the Sun. Certain areas appear brightly illuminated while others remain in shadow. These contrasts influence observation and photography. Surface details may become easier or more difficult to interpret depending on the angle of sunlight. Astronauts and scientists pay close attention to these visual conditions. Earth occasionally appears above the lunar horizon from the spacecraft's perspective. The sight provides a striking reminder of the mission's origin. Compared with the Moon beneath the spacecraft, Earth appears colourful. White cloud systems move across blue oceans and varied continents. The contrast highlights differences between the two worlds. Earth supports active weather-abundant water and life. The Moon presents a dry and largely unchanging landscape. As preparations continue, the crew rehearses procedures associated with spacecraft separation and independent operations. Checklists guide these activities. Every switch position, communication sequence, and system configuration receives verification. The objective is to reduce uncertainty as much as possible before more demanding mission phases begin. The quiet rhythm of lunar orbit allows time for careful observation. Craters reveal layers of geological history. Ridges trace ancient structural changes. Plains record episodes of volcanic activity that occurred billions of years earlier. Scientists on Earth anticipate the information that direct exploration may soon provide regarding these features. By the conclusion of this period, Apollo 11 has become fully established within the Moon's immediate environment. The crew understands the terrain below with greater familiarity than was possible during approach. Navigation systems have demonstrated accuracy. Spacecraft operations continue successfully. The Moon is no longer a distant destination or even merely a nearby world. It has become the operational setting in which every task now occurs. Orbit after orbit, the spacecraft circles above the ancient surface, gathering information and refining preparations, while remaining entirely within the gravitational embrace of the Moon. Apollo 11 continues circling the Moon, while preparations for descent reach their final stages. The time arrives when the mission must transition from observation and orbital operations to the attempt that defines its central objective. Two spacecraft that have travelled together since departing Earth will soon separate. One will remain in orbit above the Moon. The other will begin a controlled journey toward the surface. The lunar module named Eagle is designed specifically for this purpose. Unlike the command module, which must support long-distance travel and survive return to Earth, Eagle exists solely to operate in space and within the lunar environment. Every aspect of its design reflects this specialized role. Engineers remove features unnecessary for atmospheric flight and concentrate on propulsion, visibility, landing capability, and life support. Inside the spacecraft, Neil Armstrong and Edwin Aldrin transfer into the lunar module and begin activating systems. Checklists guide the process. Instruments are examined carefully. Communications links are verified. Electrical systems, guidance equipment, propulsion components, and environmental controls all require confirmation before separation can occur. Meanwhile, Michael Collins remains aboard the command module. His responsibilities continue to be essential. He will maintain operations in lunar orbit while Eagle descends to the surface. Throughout the mission, the command module serves as the vehicle that ultimately carries the crew home to Earth. Separation occurs after extensive preparation. Mechanical connections release. The two spacecraft slowly move apart. Eagle now becomes an independent vehicle orbiting the Moon. The separation appears gentle, but it represents a major transition. For the first time during the mission, the crew is divided between two different spacecraft operating independently. Following separation, both vehicles perform inspections. Collins observes Eagle from the command module and reports its condition. Armstrong and Aldrin examine their own systems. These checks help ensure that no unexpected issues have developed during the separation process. The lunar module's appearance reflects its unique purpose. Angular surfaces expose structural elements, landing legs, and external equipment, give it a form unlike conventional aircraft. In the vacuum of space, aerodynamic considerations are irrelevant. Function determines shape. Every kilogram of mass and every component serves specific operational requirements. As preparations continue, Eagle remains in lunar orbit. The astronauts verify guidance information and compare data with expected values. Navigation accuracy is crucial because the upcoming descent must place the vehicle within a carefully selected region of the lunar surface. The Sea of Tranquility remains the target. Earlier observations and analyses indicate that the area provides relatively favorable conditions for landing. Nevertheless, the Moon is not a perfectly smooth world. Craters, rocks, slopes, and uneven terrain exist throughout the landscape. Even within suitable regions, careful judgment will be necessary during the final stages of descent. The descent begins with a maneuver that changes Eagle's orbit. A rocket engine fires, reducing velocity and allowing the spacecraft to move gradually toward lower altitudes. Lunar gravity begins drawing the vehicle closer to the surface. The process unfolds according to calculations developed through years of planning and supported by data gathered throughout the mission. At first, the Moon still appears distant beneath the spacecraft. Eagle follows a path carrying it steadily downward. Guidance systems monitor altitude, velocity, orientation, and position. Computers process information and assist in controlling the trajectory. The astronauts continuously compare instrument readings with expected values. The onboard guidance computer represents a remarkable achievement for its era. By modern standards, its processing capabilities are limited, yet it performs functions essential to lunar navigation and descent. Engineers have designed both hardware and software to operate reliably under demanding conditions. The system helps manage calculations that would otherwise impose a much greater burden upon the crew. As Eagle descends, communication with mission control remains active. Controllers on Earth receive telemetry and monitor the spacecraft's progress. Telemetry provides detailed information regarding performance and status. Specialists analyze these measurements continuously, comparing actual conditions with mission plans. The lunar surface gradually reveals increasing detail. Large features visible from orbit give way to smaller structures. Individual craters become more distinct. Variations in terrain emerge. Shadows provide clues regarding slopes and elevations. The visual environment changes steadily as altitude decreases. During descent, an unexpected challenge develops. The guidance computer begins displaying alarms. These warnings attract immediate attention because they indicate that the computer is receiving more information than it can process comfortably. Engineers in mission control rapidly evaluate the situation. Observations indicate that the computer continues performing its essential functions despite the alarms. After careful assessment, controllers determine that the descent can proceed. The incident illustrates the importance of preparation and expertise. Years of training allow astronauts and controllers to interpret information quickly and respond appropriately. The alarms do not automatically require aborting the mission. Instead, understanding the underlying behavior of the system permits informed decision-making. As Eagle approaches lower altitudes, the landing area becomes increasingly visible. The guidance system continues directing the spacecraft toward the planned location. However, visual observations reveal conditions that require attention. The area immediately ahead contains more rocks and uneven terrain than expected. A fully automatic landing at that exact spot could introduce unnecessary risk. Armstrong therefore assumes greater manual control over portions of the descent. He guides the spacecraft toward a more suitable area nearby. This decision reflects both training and real-time observation. The objective remains the same: achieve a safe landing while preserving sufficient fuel reserves. The final minutes require careful management of altitude, speed, and position. The spacecraft moves slowly across the surface while descending. dust begins to respond to the engine exhaust. Fine lunar material is pushed outward, creating visual effects near the ground. Unlike Earth, the absence of an atmosphere influences how this material behaves. Fuel levels become an important consideration. Eagle carries only a limited quantity available for landing operations. Mission Control monitors remaining reserves closely. The astronauts continue searching for an acceptable landing location, while maintaining stable control of the vehicle. The surface now fills much of the view. Craters, rocks, and subtle terrain variations become immediately relevant rather than distant geological features. The descent has transformed from a navigational exercise into a direct interaction with the lunar environment. By the end of this phase, Eagle is moving only a short distance above the Moon. Years of engineering training and planning have brought the spacecraft from Earth to the threshold of landing. The vehicle remains under control, the crew remains focused, and the lunar surface waits directly below. Every observation, every calculation, and every decision now centers upon the final approach toward a world no human has ever touched. The final stage of descent unfolds slowly and deliberately. Eagle moves only a short distance above the lunar surface, yet these last moments demand exceptional attention. The spacecraft has traveled hundreds of thousands of kilometers. From Earth crossed cislunar space, entered orbit around the Moon, and descended through the lunar environment. Now the objective becomes simple in description, but difficult in execution, achieving a safe landing. Neil Armstrong and Edwin Aldrin monitor instruments while observing the terrain below. The lunar surface appears unlike any landscape on Earth. There is no vegetation, no flowing water, and no atmosphere softening distant features. Craters of various sizes cover the region. Rocks cast sharp shadows. Sunlight illuminates the terrain, directly creating strong contrast between bright and dark areas. The lunar module continues descending under rocket power. Unlike an aircraft, it cannot glide. Every aspect of its motion depends upon controlled thrust from its descent engine. Small adjustments influence position, velocity, and orientation. The spacecraft must reduce its downward movement gradually while remaining stable. As altitude decreases further, dust on the surface begins responding more noticeably to the engine exhaust. The Moon possesses a layer of loose material called regolith. Regolith consists of broken rock fragments, dust and debris created through billions of years of impacts. In the absence of weather and flowing water, these materials accumulate and remain largely undisturbed. Engine exhaust pushes some of this fine material outward. The resulting movement creates visual challenges. Dust begins to obscure certain surface details. The astronauts must rely upon a combination of instruments, experience and observation, while continuing the descent. Conditions differ from those encountered in aircraft operations on Earth because the lunar environment lacks an atmosphere. The landing legs extend beneath the spacecraft, ready to absorb contact with the surface. Sensors mounted near the legs are designed to indicate when touchdown is imminent. Guidance information continues updating. Fuel reserves remain under careful observation. Every remaining second matters. Mission Control follows the descent closely from Earth. Specialists examine telemetry transmitted from Eagle. Information concerning altitude, velocity, fuel status, and system performance arrives continuously. Communication delays remain brief but noticeable compared with ordinary conversations on Earth. Despite the distance, controllers and astronauts function as parts of a coordinated operational effort. The selected landing area lies within the Sea of Tranquility. Earlier missions and observations suggest that this region offers relatively favorable conditions for a landing attempt. Even so, the actual terrain contains variations impossible to eliminate completely from consideration. The Moon is a natural landscape shaped by impacts and geological processes, not a prepared landing field. As Eagle approaches the ground, the rate of descent decreases further. The spacecraft hovers briefly while continuing forward motion. Armstrong guides it toward a suitable location, identified during the final approach. Dust continues moving beneath the vehicle, but the overall situation remains under control. Then one of the landing probes makes contact with the surface. The indication reaches the crew. A few moments later, the lunar module settles onto the moon. Motion ceases. The descent engine is shut down. Eagle is no longer a spacecraft descending toward the lunar surface. It has become a stationary structure resting upon another world. The landing occurs on July 20th, 1969, according to Coordinated Universal Time. For the first time in human history, a crewed vehicle has landed successfully on the moon. Inside the cabin, the immediate response is not celebration but procedure. The astronauts begin a series of checks designed to confirm the condition of the spacecraft. Systems are evaluated carefully. Engineers on Earth review incoming data. Stability power supplies, communications, and life support functions all require verification. A successful touchdown represents an important achievement, but operational discipline remains essential. The moon beneath Eagle presents conditions unlike those of Earth. Gravity is significantly weaker. Measurements indicate that lunar gravity is approximately 1/6 as strong as Earth's gravity. This difference will influence movement, equipment handling, and every activity performed outside the spacecraft. The absence of a substantial atmosphere affects many aspects of the environment. There is no wind. Dust remains where it settles unless disturbed directly. Sound cannot travel through the vacuum outside the spacecraft. Temperature conditions vary greatly between sunlit and shadowed regions. The lunar environment is quiet, stable, and physically demanding. As the astronauts continue post-landing procedures, they observe their surroundings through the spacecraft windows. The view reveals a gently undulating landscape covered by fine material and scattered rocks. Small craters punctuate the terrain. Distant features extend toward the horizon, which appears closer than many people might expect because of the moon's smaller size compared with Earth. Scientists later examined photographs and observations from the landing site in considerable detail. The region provides valuable information about lunar geology. The surface materials visible around Eagle reflect a long history of impacts and environmental conditions unique to the moon. The landing itself becomes one of the most thoroughly documented events in the history of exploration. Telemetry records, communication transcripts, photographs, tracking information, engineering data, and observations from multiple organizations contribute to a detailed understanding of what occurred. The event is observed directly by large audiences around the world through television broadcasts and other media. Yet within the spacecraft, the reality remains practical rather than symbolic. The mission continues. Landing is not the final objective. Surface operations still lie ahead. Equipment must be prepared. Spacesuits require configuration. Checklists guide every action. The astronauts proceed methodically through tasks developed during years of planning and training. The lunar module demonstrates the effectiveness of its design. It has transported 2 astronauts safely from lunar orbit to the surface. The landing gear supports the vehicle securely. Internal systems continue functioning. Communications with Earth remain stable. The spacecraft now serves as both workplace and shelter within an environment fundamentally different from Earth. Outside, the Sea of Tranquility remains unchanged. Sunlight illuminates the surface. Shadows stretch across craters and rocks. The landscape appears ancient, preserving evidence of events that occurred across billions of years. No sign indicates that human beings have arrived except for the presence of Eagle itself. For the first time, a crewed spacecraft rests upon the moon. The long descent has ended. The uncertainties associated with landing have been resolved. Beneath the lunar module lies solid lunar ground. Around it extends the quiet surface of another world. Apollo 11 has successfully completed one of the most demanding phases of the mission and established a human presence, however temporary, upon the Moon. After the landing is complete and the lunar module has been confirmed to be operating properly, attention shifts from the spacecraft itself to the environment immediately surrounding it. The Moon is no longer a destination viewed through windows or from orbit. It is now the ground beneath the landing legs of Eagle. The next phase of the mission focuses on direct human interaction with the lunar surface and the conditions that define this unusual world. Inside the lunar module, preparations for leaving the spacecraft require time and patience. Spacesuits must be checked carefully. Life support equipment must be connected and verified. Communication systems must function reliably. Every procedure follows a sequence developed through extensive training. The astronauts understand that the environment outside provides no margin for error. Survival depends entirely upon the equipment they carry and the systems operating within their suits. The suits serve as independent life support systems. They provide oxygen for breathing, remove carbon dioxide, help regulate body temperature and protect against the vacuum outside. The lunar environment contains no breathable air and no atmospheric pressure comparable to that found on Earth. Without protection, a human being could not survive there. As preparations continue, observations of the surrounding landscape provide additional information. The surface near Eagle appears relatively level compared with many other regions visible from orbit. Fine material covers much of the ground. Rocks of different sizes are scattered throughout the area. Small craters interrupt the terrain at irregular intervals. Eventually the hatch is opened. Neil Armstrong begins moving toward the exterior. The process unfolds carefully because the spacecraft and equipment are operating in conditions never before experienced directly by human beings on another celestial body. Every movement is deliberate. A ladder attached to one landing leg provides access to the surface. Armstrong descends gradually while remaining connected to communication systems, transmitting information back to Earth. Cameras record portions of the activity. Engineers, scientists and observers around the world follow events as they occur. The final step from the ladder brings a human foot into direct contact with lunar soil. At that moment, human beings become physical participants in the lunar environment, rather than observers working from spacecraft above it. The event is historically significant, but from an operational perspective, it also marks the beginning of a series of practical tasks and scientific observations. The first impressions concern movement and surface conditions. Lunar gravity immediately influences every action. Because gravity is weaker than on Earth, body weight is greatly reduced. Mass, however, remains unchanged. Objects still possess the same resistance to motion. As a result, movement requires adjustment. Walking does not feel exactly like walking on Earth. Different techniques prove more efficient under lunar conditions. Observations indicate that the surface supports weight effectively. Earlier concerns that a spacecraft or astronaut might sink deeply into loose material are not supported by conditions at the landing site. Footprints form clearly in the fine regolith, but the surface beneath provides sufficient strength to support both astronauts and equipment. The appearance of footprints reveals interesting characteristics of lunar soil. The regolith consists of tiny fragments created through countless impacts over vast spans of time. Many particles possess sharp edges because weathering processes common on Earth are absent. Wind and flowing water do not gradually smooth these materials. As a result, footprints retain distinct shapes. Lighting conditions present unique visual challenges. The Moon lacks an atmosphere capable of scattering sunlight. On Earth, scattered light brightens shadows and softens contrasts. On the Moon, illuminated surfaces can appear extremely bright while shaded regions remain very dark. Nevertheless, reflected light from surrounding terrain often provides enough illumination to reveal details within shadows. Armstrong spends time examining the immediate area around Eagle. These early observations help confirm expectations regarding terrain stability and surface characteristics. Engineers and scientists are interested not only in broad geological questions, but also in practical considerations affecting future missions. Soon afterward, Edwin Aldrin joins Armstrong on the surface. Two astronauts now move around the landing site. Their activities remain guided by carefully prepared procedures. Although exploration naturally attracts attention, the mission is fundamentally scientific and operational. Time on the surface is limited and tasks must be completed efficiently. Movement continues to reveal the effects of reduced gravity. Small jumps and bounding motions sometimes prove effective. Nevertheless, caution remains important. A fall could damage equipment or compromise mission objectives. The astronauts therefore proceed methodically while gaining familiarity with the environment. One of the first scientific activities involves documenting the condition of the landing area. Photographs capture the position of the spacecraft, nearby surface features, and the effects of engine exhaust on the regolith. These records help scientists understand both the lunar environment and the performance of the landing system. The astronauts also deploy equipment designed to operate after their departure. Scientific instruments can continue collecting information about lunar conditions. Such devices extend the value of the mission beyond the brief period of direct human presence. Throughout these activities, communication with Earth remains continuous. Mission control monitors progress, receives observations, and provides support when necessary. The relationship between astronauts and ground teams remains essential despite the vast distance separating them. The lunar horizon contributes to the distinctive appearance of the landscape. Because the Moon is smaller than Earth, the curvature of the surface becomes noticeable over shorter distances. The horizon seems relatively close, giving the environment a different visual character from many terrestrial landscapes. Silence defines the exterior environment. Sound cannot travel through the vacuum surrounding the astronauts. Communications occur only through radio systems. Activities that would normally produce audible effects on Earth remain unheard outside the suits. The lunar surface exists in a state of remarkable stillness. The environment also preserves evidence of human activity with unusual permanence. Footprints, equipment marks, and disturbances in the regolith are not erased by wind or rain. Observations indicate that such traces may remain visible for extremely long periods, altered primarily by slow processes such as micrometeorite impacts. As surface operations continue, the astronauts gain practical experience living and working on another world. The Moon reveals itself not as an abstract object studied through telescopes, but as a physical environment with specific properties affecting movement, observation, and scientific work. Every step, every footprint, and every measurement contributes to a clearer understanding of conditions on the lunar surface. The landing site in the Sea of Tranquility now contains visible evidence of human presence, yet the surrounding landscape remains largely unchanged, extending outward in all directions beneath the bright sunlight. The astronauts move carefully across the ancient regolith, learning directly from the environment beneath their feet, while carrying out the work that brought them from Earth to the Moon. With the first movements across the lunar surface completed, and the immediate environment assessed, Apollo 11 enters a phase centered on scientific investigation. The astronauts remain within the Sea of Tranquility, operating in a limited area around the lunar module. Yet the work performed during these hours carries significance far beyond the landing site itself. Every observation, measurement, photograph, and collected sample contributes to a broader effort to understand the Moon as a physical world. Scientific exploration on Apollo 11 is necessarily constrained by time. The astronauts cannot travel great distances, nor can they examine every geological feature visible from the landing site. Mission planners therefore focus on obtaining information that offers the greatest value within the available period. Procedures are designed carefully balancing scientific objectives with operational requirements and safety considerations. Photography becomes one of the most important scientific tools. Cameras document the landscape in considerable detail. Images capture the appearance of the surface, the distribution of rocks, the texture of the regolith, and the relationship between different geological features. Photographs also preserve contextual information that helps scientists interpret samples after their return to Earth. The absence of an atmosphere influences the appearance of these images. Sunlight strikes the surface directly. Shadows remain sharp and well-defined. The contrast between illuminated and shaded regions differs from what is commonly observed on Earth. Scientists later use these photographs to study terrain characteristics and compare observations with orbital imagery obtained before the mission. The astronauts move methodically through planned activities. Equipment is deployed according to procedures refined during years of preparation. Each action serves a purpose. Mission planners recognize that opportunities for direct lunar exploration are limited, making efficient use of time essential. One of the scientific instruments placed on the surface is designed to reflect laser beams transmitted from Earth. This reflector contains carefully arranged mirrors that return incoming light toward its source. Observatories on Earth can direct laser pulses toward the Moon and measure the time required for the light to return. These measurements provide extremely accurate information about the distance between Earth and the Moon. The deployment of such equipment illustrates an important aspect of the mission. Apollo 11 is not simply a demonstration of transportation technology. It is also a scientific expedition intended to expand knowledge through direct investigation and long-term observation. Another instrument studies the solar wind. The solar wind consists of charged particles flowing outward from the Sun through the solar system. Because the Moon lacks a substantial atmosphere and global magnetic field comparable to Earth's, solar particles can interact directly with the surface. Collecting information about these particles helps scientists understand both the Sun and the lunar environment. While instruments are being installed, geological observations continue. The astronauts examine rocks and surface materials visible around the landing site. Scientists have prepared them for this work through extensive training on Earth. Although neither Armstrong nor Aldrin is a professional geologist, both have learned techniques for recognizing and documenting significant features. The regolith attracts particular attention. Observations confirm that it behaves differently from many familiar materials on Earth. Fine particles adhere to equipment and boots. Footprints remain clearly visible. Surface disturbances produce distinct patterns. These characteristics provide clues regarding the long-term processes that have shaped the lunar landscape. Sample collection becomes a major activity. The astronauts gather rocks and soil from different locations near the lunar module. Some samples are obtained quickly as a precautionary measure early in the surface operations. This approach ensures that valuable material will be returned even if later activities encounter difficulties. Additional samples are selected more carefully. Astronauts examine individual rocks and document their locations before collection. Context is important because the scientific value of a sample often depends upon understanding where it originated and how it relates to surrounding features. The rocks visible around the landing site vary in size, shape, and appearance. Some display evidence of impact processes. Others reflect volcanic origins associated with ancient flows of molten material. Scientists anticipate that laboratory analysis on Earth will reveal far more information than can be determined through visual inspection alone. The Moon serves as a geological archive. Unlike Earth, it lacks active weather systems capable of erasing many surface features. Rivers do not carry sediments across the landscape. Wind does not reshape terrain on a large scale. Vegetation does not cover older structures. As a result, rocks and surface formations often preserve evidence of events that occurred billions of years ago. Observations made during Apollo 11 support the idea that impacts have played a major role in shaping the lunar surface. Craters of various sizes are visible throughout the region. Many rocks appear fractured or altered by collision processes. Scientists view these findings as part of a larger effort to understand the history of the Moon, and by extension the early history of the solar system. The astronauts also document the behavior of dust and soil during movement and equipment operations. Such information has practical value. Future missions will depend upon understanding how lunar materials interact with machinery, tools, and spacesuits. Observations from Apollo 11 therefore contribute both to scientific knowledge and to operational planning. Throughout the surface activities, communication with Earth remains continuous. Scientists and engineers listen carefully to descriptions provided by the astronauts. Real-time observations complement photographs and collected samples. Together, these sources of information create a more complete picture of conditions at the landing site. The lunar module remains visible nearby throughout most of the work. Its presence provides a constant reference point and a reminder that all activities must occur within the limits established by available time, oxygen, power, and mission planning. Surface exploration is extensive for its duration, but it remains focused and deliberate. As the period of scientific investigation progresses, containers gradually fill with samples destined for Earth. Instruments stand deployed on the lunar surface. Photographs accumulate. Measurements are completed. Each task adds another layer of understanding to humanity's knowledge of the Moon. The Sea of Tranquility continues to appear quiet and unchanged beyond the immediate area of activity. Yet through observation and investigation, the astronauts reveal details hidden within the landscape. What appears at first to be a simple expanse of dust and rock becomes a source of information about impacts, volcanism, solar influences, and planetary history. The scientific work of Apollo 11 transforms the landing site from a destination into a field laboratory, where careful observation and sample collection begin uncovering the deeper story recorded in the lunar surface. As the scientific activities continue around the lunar module, increasing attention focuses on the material that covers and composes the lunar surface itself. The rocks and dust collected during Apollo 11 are not merely souvenirs from another world. They are physical records of lunar history. Each fragment contains information about processes that have shaped the Moon over immense spans of time. Understanding these materials becomes one of the most important scientific outcomes of the mission. The surface of the Moon appears simple at first glance. Much of the landscape is covered by fine grey material, interrupted by rocks, small craters, and occasional larger features. Yet closer examination reveals considerable complexity. The ground beneath the astronauts' boots consists of regolith, a layer formed through billions of years of impacts from meteorites, asteroids, and smaller particles arriving from space. Unlike Earth, the Moon lacks the environmental processes that constantly reshape many landscapes. There is no rain to erode rocks. There are no rivers transporting sediments. There is no wind carrying particles across great distances. As a result, impacts become the dominant force influencing the surface. Every collision breaks existing material into smaller fragments, gradually creating the layer of dust and debris observed around the landing site. The regolith varies in particle size. Some pieces are large enough to be recognized easily as individual rock fragments. Others are extremely fine, resembling powder. Observations made during surface operations indicate that the material can retain clear footprints and equipment marks. This behavior reflects both the physical properties of the particles and the absence of weather capable of disturbing them afterward. The astronauts collect samples from several locations near Eagle. Some specimens consist primarily of loose soil. Others are individual rocks selected because of their appearance, texture, or position within the landscape. Every sample is placed into carefully designed containers intended to preserve its condition during the return journey to Earth. Scientists understand that the true value of these materials will emerge only after detailed laboratory examination. Instruments available on Earth can determine chemical composition, mineral content, crystal structure, and age with much greater precision than is possible during a brief surface expedition. Nevertheless, observations made at the landing site provide essential context for later analysis. The Sea of Tranquility is of particular geological interest because it belongs to a category of lunar terrain known as mare regions. The term originates from early astronomers who mistakenly believed the dark areas visible on the Moon contained seas. In reality, these plains consist largely of solidified volcanic rock. Long ago, molten material emerged from the lunar interior and spread across portions of the surface, before cooling and hardening. The rocks collected during Apollo 11 help confirm this interpretation. Analyses performed after their return indicate that many samples contain basalt, a volcanic rock also found on Earth. The presence of basalt supports the conclusion that volcanic activity played an important role in shaping certain regions of the Moon's surface during its early history. At the same time, the samples reveal evidence of impacts. Many rocks display signs of intense forces associated with collisions. Some contain fractures and structures produced by shock waves, generated when large objects strike the lunar surface. These findings reinforce the understanding that impacts have influenced lunar geology for billions of years. One of the most significant aspects of the returned material involves age determination. Scientists use radiometric dating techniques to estimate when rocks formed. Radiometric dating relies on the predictable behavior of certain radioactive elements and their decay products. By measuring these substances, researchers can estimate the age of geological samples. Results obtained from Apollo 11 materials indicate that parts of the lunar surface are extremely ancient. Many rocks formed billions of years ago. These ages provide important information not only about the Moon, but also about the early history of the solar system. Because Earth's surface is constantly reshaped by tectonic activity, erosion, and other processes, many very old geological records have been altered or destroyed. The Moon preserves evidence from periods that are much more difficult to study on Earth. The dust itself also proves scientifically valuable. Microscopic examination reveals particles with sharp, irregular shapes. On Earth, weathering often rounds and smooths mineral grains over time. On the Moon, the absence of wind and water allows many fragments to retain angular forms. This characteristic helps explain some of the behavior observed during surface operations. Scientists also study the chemical composition of lunar soil. Measurements indicate the presence of elements common in rocky planetary bodies, including oxygen, silicon, aluminum, magnesium, calcium, and iron. The proportions of these elements provide clues regarding the formation and evolution of the Moon. The samples returned by Apollo 11 represent only a small quantity of material compared with the vast mass of the Moon itself. Nevertheless, they establish a foundation for future research. Later Apollo missions will collect additional samples from different regions, allowing scientists to compare geological conditions across a wider range of environments. The materials from the Sea of Tranquility serve as the first direct evidence obtained by human explorers. The collection process itself demonstrates the practical challenges of geological work on another world. Reduced gravity influences movement and tool handling. Spacesuits limit flexibility. Time remains constrained by mission requirements. Despite these limitations, the astronauts gather a scientifically meaningful set of specimens that exceeds the minimum objectives established before the mission. Back on Earth, laboratories prepare to receive the samples under carefully controlled conditions. Scientists recognize that contamination must be minimized. Procedures are developed to preserve the integrity of the material and ensure reliable analysis. Every gram of lunar rock and soil is treated as a valuable scientific resource. The landscape surrounding Eagle continues to appear quiet and unchanging during these activities. Yet within the collected samples lies evidence of ancient volcanism, repeated impacts, chemical evolution, and geological processes extending back billions of years. What seems at first to be a simple surface of grey dust and scattered stones contains a detailed record of lunar history. By gathering these materials and returning them to Earth, Apollo 11 provides something more enduring than photographs or observations alone. The mission delivers physical pieces of the Moon itself into the hands of researchers. These rocks and soils become direct evidence, allowing scientific questions to be examined through measurement rather than speculation. The surface of the Sea of Tranquility thus becomes not only the site of humanity's first lunar landing, but also the source of a collection that fundamentally expands understanding of the Moon and its place within the history of the solar system. As Apollo 11 completes its work on the lunar surface and prepares for the journey home, another dimension of the mission becomes increasingly important. Beyond the landing itself, beyond the photographs, and beyond the collected rocks and soil, lies the question of evidence. How is the mission documented, verified, and understood? The answer emerges through a vast network of observations, measurements, records, physical materials, and independent confirmations that together create one of the most thoroughly documented events in human history. The evidence for Apollo 11 does not originate from a single source. It comes from many different systems operating simultaneously. Some records are generated by the spacecraft themselves. Others come from tracking stations on Earth. Additional information is collected by scientific institutions, government agencies, engineers, radio operators, and later researchers. Each source contributes a different perspective on the mission. One important category of evidence consists of telemetry data. Telemetry is the automatic transmission of measurements from a distant vehicle to observers elsewhere. Throughout the mission, thousands of pieces of information flow continuously from Apollo 11 to Earth. Temperatures, pressures, fuel quantities, electrical performance, navigation, status, engine, behavior, communication signals, and many other measurements are recorded. These data streams are not simply displayed temporarily and then forgotten. They are preserved, analyzed, compared with expectations, and incorporated into technical reports. Engineers use them to evaluate spacecraft performance. Scientists use them to understand mission operations. Historians later use them to reconstruct events in remarkable detail. Communication records provide another major source of evidence. Conversations between the astronauts and mission control are transmitted, recorded, and archived. These records document operational decisions, observations, technical issues, and routine activities throughout the mission. Because communications occur continuously during many phases of flight, they create an extensive chronological account of what happens. Photography adds a visual dimension to the documentation. Cameras carried aboard the spacecraft and used on the lunar surface produce large numbers of images. These photographs show the spacecraft, the landing site equipment, surface features, and the activities of the astronauts. The images can be examined repeatedly and compared with geological observations, mission plans, and later studies of the landing area. Motion picture and television recordings contribute additional documentation. Portions of the mission are broadcast to audiences around the world. Millions of people observe events as they occur. Although the quality of some recordings reflects the technology available at the time, they nevertheless provide direct visual evidence of mission activities. Tracking networks represent another critical component. Apollo 11 is not observed solely by NASA. Radio signals from the spacecraft are monitored by facilities in multiple locations. Large antennas receive transmissions and help determine the spacecraft's position and trajectory. These measurements allow independent verification of the mission's movement through space. The Deep Space Network plays a particularly important role. This system of large radio antennas supports communication with distant spacecraft. During Apollo 11, stations located in different regions of Earth help maintain contact as the planet rotates. Observations from these facilities confirm the spacecraft's path and operational status. Independent observers also contribute evidence. Amateur radio operators track transmissions. Astronomers monitor aspects of the mission. International organizations follow developments closely. The mission takes place in a global environment where many individuals and institutions possess both the capability and the motivation to observe events directly. The returned lunar samples provide perhaps the most tangible evidence of all. Unlike photographs or radio signals, rocks and soil can be examined physically. Scientists around the world study these materials. Their chemical composition, mineral content, age, and structural characteristics reveal origins consistent with the lunar environment. Analyses performed over subsequent decades repeatedly support the conclusion that the samples come from the Moon. The characteristics of the materials differ in important ways from ordinary terrestrial rocks. Later comparisons with samples returned by robotic missions and lunar meteorites strengthen this understanding further. The laser reflector deployed during surface operations offers another form of continuing verification. Decades after Apollo 11, observatories on Earth continue directing laser beams toward the reflector and receiving the returning signals. These measurements provide ongoing evidence that the instrument remains at the landing site. The landing area itself becomes a subject of later observation. Advances in space exploration eventually allow spacecraft to photograph portions of the lunar surface at much higher resolution than was possible during the Apollo era. Images reveal features consistent with the presence of landing hardware equipment locations and paths created by astronaut movement. Observations indicate that these features match expectations derived from mission records. Scientific reports generated after the mission add further documentation. Engineers publish analyses of spacecraft performance. Geologists publish studies of lunar materials. Medical specialists examine physiological data gathered during the mission. Together, these publications create an extensive body of technical literature describing what occurred and what was learned. The existence of such diverse evidence is important because it reduces reliance upon any single source. Photographs support telemetry. Telemetry supports tracking data. Tracking data supports communication records. Communication records support operational reports. Lunar samples support geological conclusions. Independent observations support official records. Multiple forms of evidence reinforce one another. From a historical perspective, Apollo 11 occurs during a period of intense international attention. Rival nations possess sophisticated scientific and technical capabilities. The mission is observed globally. Any substantial inconsistency would likely attract scrutiny from experts across many disciplines. Instead, observations from independent sources remain consistent with the documented events. The question of what really happened during Apollo 11 can therefore be approached through evidence rather than assumption. Records indicate that a spacecraft traveled from Earth to the Moon. Tracking systems observed its trajectory. Communications documented operations. Astronauts conducted activities on the lunar surface. Samples were collected and returned. Scientific instruments were deployed. Subsequent observations continue to support these conclusions. The mission becomes one of the best documented explorations ever undertaken. Evidence exists in physical materials, recorded signals, archived documents, scientific analyses, photographs, films, and ongoing measurements. No single item stands alone. Together they form an interconnected body of information extending across decades. As Apollo 11 moves from immediate experience into history, verification becomes part of its legacy. The truth of the mission is preserved not through memory alone, but through a remarkable accumulation of records and observations: the landing site, the returned rocks, the communication archives, the tracking data, and the continuing scientific studies all contribute to a detailed and enduring account of what occurred when human beings first landed on the moon. Apollo 11 eventually leaves the lunar surface behind. The scientific work has been completed, samples have been collected, instruments have been deployed, and observations have been recorded. The mission that began beneath Earth's atmosphere and progressed through launch, orbital flight, cislunar travel, lunar orbit, descent, landing, and surface exploration, now enters its final historical perspective. The focus shifts from the immediate events themselves to their enduring significance and to what is firmly known today about humanity's first landing on the moon. The ascent from the lunar surface begins with the upper portion of the lunar module. The lower descent stage remains behind as a platform resting on the moon. A rocket engine carries Neil Armstrong and Edwin Aldrin back into lunar orbit, where they reunite with Michael Collins aboard the command module. This operation succeeds according to mission plans. The crew is once again together within a single spacecraft. After docking and transferring equipment and samples, the lunar module is no longer needed. Attention turns toward the return journey. The spacecraft performs maneuvers that allow it to leave lunar orbit and begin traveling back toward Earth. The route home differs from the path that originally brought Apollo 11 to the moon, yet the same principles of navigation, communication, and spacecraft operations continue to guide the mission. During the return voyage, the astronauts remain occupied with observation system monitoring and routine activities. Earth gradually grows larger in the spacecraft windows. The distant globe that had appeared small during the journey outward now becomes increasingly prominent. Continents, oceans, and cloud systems once again reveal recognizable detail. The final stage of the mission involves re-entry into Earth's atmosphere. This process requires careful control because the spacecraft returns at extremely high velocity. The command module enters the atmosphere at a precise angle. Too steep an entry could expose the vehicle to excessive heating and deceleration. Too shallow an entry could cause it to skip outward rather than descend properly. Protective materials on the exterior of the capsule absorb and carry away heat generated during re-entry. Temperatures outside become extremely high as atmospheric friction converts kinetic energy into heat. The design of the spacecraft allows the crew to remain protected within the capsule while these conditions occur. Eventually, parachutes deploy and slow the descent. Apollo 11 lands safely in the Pacific Ocean. Recovery forces retrieve the astronauts and spacecraft. The journey that began on Earth and extended to another world concludes once again on the planet from which it departed. From a scientific perspective, the mission produces results that extend far beyond the days during which it takes place. The lunar samples become subjects of study for decades. New analytical techniques developed long after 1969 continue extracting information from the material returned by Apollo 11. Observations made during the mission contribute to a growing understanding of lunar geology and the history of the solar system. The mission also demonstrates technologies and operational methods previously unproven at such a scale. Precision navigation across hundreds of thousands of kilometers rendezvous in lunar orbit sustained human activity on another celestial body, and safe return to Earth all become demonstrated realities rather than theoretical possibilities. The broader historical significance of Apollo 11 emerges from this combination of exploration science and engineering. Human beings have long observed the Moon from Earth. For thousands of years it remained a distant object visible in the night sky, but inaccessible to direct investigation. Apollo 11 transforms that relationship. The Moon becomes a place that human beings have physically visited, studied, and sampled. The mission also reveals the importance of cooperation among many disciplines. Engineers, scientists, technicians, physicians, mathematicians, computer specialists, managers, and astronauts all contribute to the outcome. No single individual creates the achievement alone. Apollo 11 reflects the combined effort of a vast network of people working toward a common objective. Over time, public discussion of the mission occasionally includes claims that the landing did not occur as documented. Such claims have been examined extensively. The available evidence remains consistent with the historical record of a successful lunar landing. Lunar samples exist and have been studied internationally. Tracking records document the spacecraft's trajectory. Communications archives preserve operational details. Photographs and films record activities. Later observations of the landing site align with mission reports. The strength of the evidence lies not in any single photograph, recording, or document. It lies in the agreement among many independent sources. Geological findings support operational records. Tracking data supports navigation reports. Physical artifacts support historical documentation. Decades of examination have reinforced rather than weakened the conclusion that Apollo 11 landed successfully on the Moon. The mission's scientific legacy continues as well. Modern understanding of lunar formation geological history, impact processes, and planetary evolution benefit significantly from Apollo-era research. Observations indicate that the Moon likely formed following a major event early in Earth's history. Lunar samples help scientists evaluate and refine models concerning this process. Research remains active and some details continue to be investigated, but Apollo 11 contributes foundational information to these efforts. The landing site itself remains on the Moon. The descent stage, scientific equipment, footprints, and other traces of human activity persist in the absence of weather. Observations indicate that many of these features remain visible decades after the mission. They serve as physical reminders of a brief period when human beings worked on the lunar surface. Viewed from the perspective of history, Apollo 11 represents a carefully documented event rather than a legend. Its reality is preserved through engineering records, scientific evidence, physical samples, and continuing observation. The truth of what happened does not depend upon memory alone. It rests upon measurable facts accumulated before, during, and after the mission. The story that begins with Earth proceeds outward through space, reaches the lunar surface, and returns home, ultimately reveals something both simple and profound. Human beings built machines capable of crossing the distance between worlds. They landed on the Moon, conducted scientific work, collected evidence, and returned safely. The mission remains one of the most significant achievements in exploration because it combines imagination with measurable reality, curiosity with discipline, and ambition with careful verification. The truth about the first moon landing is therefore not hidden within mystery. It exists within the extensive record left behind by Apollo 11 itself. The spacecraft flew, the astronauts landed, the samples returned, and the evidence endured. Across the decades that follow, observations, research, and documentation continue to support the same conclusion. Human beings truly reached the Moon and came home again. The story gradually settles after the return to Earth. The excitement surrounding the mission fades into history, yet the evidence remains. Boxes containing lunar rocks and soil move into laboratories. Engineers organize technical records. Scientists begin years of careful study. Photographs are catalogued. Communication recordings are preserved. The work of understanding continues long after the spacecraft itself has completed its journey. The Moon remains where it has always been, circling Earth in a steady rhythm. From the ground it appears much as it did before Apollo 11. Its familiar phases continue to change across the month. Bright lunar light still reflects from ancient plains, mountains, and craters. Yet knowledge of the Moon is no longer based solely on distant observation. Human footprints, scientific instruments, and collected samples have connected the two worlds in a direct and lasting way. The mission leaves behind more than physical traces. It demonstrates how careful planning, engineering, and scientific inquiry can transform an idea into reality. Thousands of individual tasks, each seemingly small on its own, combine into a journey across space. The achievement emerges not from a single moment, but from years of steady work carried out by many people. The lunar samples continue revealing information long after their return. New instruments and analytical methods allow later generations of researchers to study materials collected during Apollo 11 in ways that were impossible in 1969. The rocks remain valuable because they preserve records from an ancient world, largely unchanged by weather or flowing water. On the Moon, the landing site rests in silence. The descent stage remains where it touched down. Footprints still mark portions of the regolith. Scientific equipment continues to occupy its place on the surface. Sunlight and shadow pass across the landscape while the surrounding terrain remains much as it was when the astronauts departed. Back on Earth, the mission becomes part of the broader story of exploration. It joins earlier voyages across oceans, deserts, mountains, and polar regions. Yet it also stands apart because it extends exploration beyond Earth itself. Apollo 11 shows that another world can be reached, studied, and understood through direct human effort. The truth of the first moon landing rests quietly within the records, the rocks, the photographs, the measurements, and the enduring evidence left behind. The journey begins on Earth, reaches the Moon, and returns home. Decades pass, technology changes, and generations come and go, yet the essential facts remain unchanged. Human beings travelled across space, landed on the lunar surface, carried out scientific work, and safely returned. The Moon continues its orbit above Earth, and the story of Apollo 11 remains preserved in both history and science.